In the name of Allah, the Merciful, the Beneficent. Assalamu alaikum, everyone. My name is Kashiful Khair, and I am currently pursuing my Master's in Chemistry at the University of Management and Technology. Today, I'm excited to share with you insight from a captivating review article on the topic Renewable Energy to Green Hydrogen, a review of main resources, routes, processes, storage, and non-zero emission target. This comprehensive review article was conducted under the guidance of Dr. Hammad Majeed, the head of the Chemistry Department at University of Management and Technology. With his expertise and leadership, they have played pivotal role in shaping this exploration into the intricate world of renewable energy and its conversion into green hydrogen. So as we delve into the review article, I'll be exploring key aspects such as resource routes, processes, storage mechanism, and its crucial pursuit of a non-zero emission target. So without any further ado, let's embark on this journey together and examine the pathways, challenges, and opportunities outlined in this enlightened review article. Before moving toward the main part of my article, let's have a look at the presentation layout. Firstly, I will explain the abstract of my article. After that, the article starts by setting the stage for the critical examination of renewable energy to green hydrogen process in the topic named as Introduction. I'll uncover the significance of this research in the broader context of sustainable energy and the ever-growing demand for the eco-friendly alternatives. After the introduction, I'll tell you the method of producing green hydrogen, and I have explored the various methods in the production of green hydrogen. I explore how these methods can be used to produce hydrogen, and each method presents unique challenges and opportunities contributing to the intricate tapestry of sustainable hydrogen production. The method includes production of hydrogen from solar energy, wind energy, water electrolysis, ammonia decomposition and ammonia cracking, geothermal energy, and from biomass. After the methods, I'll explain or I'll shift my focus to a critical aspect of the green hydrogen landscape, which is known as a storage of hydrogen. For understanding how we store this valuable resource is key to its efficient utilization, and I'll uncover the methods, technologies, and consideration that came into the efficient utilization. After the storage of hydrogen, I'll move toward the environmental impact, which is an integral part of my analysis. After the environmental impact, I'll tell you about the non-zero emission target. Basically, non-zero emission target refers to the achieving an overall balance between greenhouse gas emission produced and greenhouse gas emission taken out of this atmosphere. And moving forward, my exploration will touch upon a crucial target, achieving a non-zero emission profile, and I'll discuss the significance of this target, its challenges, its advancement needed to realize for the future, where hydrogen production is truly environment friendly. And at last, I'll wrap up my journey with a comprehensive conclusion. And it will serve as a synthesis of my findings, emphasizing key takeaways, highlighting potential areas for future research, and ultimately summarizing the contribution of this review article to the field of renewable energy to green hydrogen. Basically, my videos has two parts. In the first part of my presentation, I'll introduce the review article on the renewable energy to green hydrogen production, starting with the abstract introduction, and then I'll cover some method of producing green hydrogen. So let's start with the abstract. As we all know that in the recent age, we all have delved into the promising realm of hydrogen as a sustainable energy resource, addressing the pressing need of eco-friendly alternatives. Basically, the attraction of or the extraction of hydrogen from renewable resources not only prevents these valuable resources from ending up into landfills or undergoing costly treatments, but it also plays a pivotal role in shaping a more sustainable energy landscape. However, it's crucial to note that many methods of converting renewable to hydrogen are still in their early stages, and they require substantial development to establish themselves as integral component of sustainable energy strategies. In my analysis, I provide a comprehensive examination of renewable to hydrogen technologies, taking into account technical, economical, ecological, and social aspects. This examination also summarizes the current status of 6 technologies that are shedding light on the advancement outlined in the existing literature. Through this in-depth exploration, I have also identified various information gaps, research directions, opportunities, and potential improvements that are particularly in the areas of efficiency, greenhouse gas emission, manufacturing cost, hydrogen-based mobility, and public acceptability. The outcome of these studies are paramount for facilitating the safe incorporation of hydrogen into extensive energy facilities, paving the way for a more sustainable and secure energy future. So let's move towards the main introduction of my article. Basically, in our quest for a sustainable future, hydrogen has emerged as a beacon of hope, offering unparalleled potential to reshape our energy landscape. As we stand as the precipice of a pivotal era in the environmental consciousness, the importance of hydrogen cannot be overstated. At the turn of the 20th century, a resounding call to action impact of climate change, and in response, hydrogen has risen to the forefront, providing itself as a key player in this global initiative. So here a question arises, why is hydrogen hailed as the premier fuel for our generation? The answer lies in its remarkable attributes and its ability to align seamlessly with the principle of sustainability. Hydrogen represents more than just a fuel. It embodies a paradigm shift towards cleaner, more efficient energy system. Traditionally valued a commodity gas and feedstock, hydrogen has transacted its conventional roles. It stands as a clean and versatile energy carrier, which is capable of being derived from a spectrum of resources, including hydrogen-containing compounds, waste materials, and biomass. This versatility not only ensures a diversified and sustainable supply, but also positions hydrogen as a catalyst for the essential energy transformation on our planet, so it is urgently needs. Basically, the integration of hydrogen with renewable energy sources on a large scale mark a monumental stride towards environmental sustainability. Its adaptability enhances the flexibility of our energy system, aligning production more closely with demand pattern. The temporal and spatial flexibility of hydrogen allows for storage, delivery, and usage on scale ranging from daily to seasonal, unshading in a review era of energy accessibility and reliability. But what sets hydrogen apart and deals in the fuel of our generation? The answer to this question, its role as a bridge between intermittent renewable resources such as solar and wind and consistent energy demand is pivotal. This hybridization not only strengthens the contribution of renewable but also addresses the challenges posed by the unpredictable nature of these resources. So in this presentation, I'll delve into a critical aspect of contemporary global efforts in environment sustainability, specifically focusing on the role of hydrogen in mitigating objectives, in mitigating greenhouse gas emissions and its alignment with the United Nations Sustainable Development Objectives. Since the late of 20th century, there has been a concerted global initiative to address the urgent need to reduce greenhouse gas emissions and limit the rise in the world's average temperature to 3 degrees Celsius above pre-industrial level. So due to this reason, hydrogen has emerged as a validated solution in its initiative, offering a clean and versatile energy carrier. Furthermore, hydrogen's adaptability enhances the flexibility of energy system, aligning with its energy production more closely with demand patterns. Its temporal and spatial flexibility allows for a daily to seasonal storage as well as local and international delivery, extended its utility beyond energy production. So it recognizes the imperative for cleanest energy systems. Nations worldwide are focusing research efforts on deploying hydrogen as a catalyst for sustainable energy systems. Collaborative plans and roadmaps involves manufacturer and hydrogen organizations are being formulated to decrease carbon emission with a specific focus on categorizing hydrogen utilization into 4 stationary applications. The first one is massive power production. The second one is manufacturing sites. The third one is residential building. And the other one is infrastructures. So this approach aims to address the challenges of reducing greenhouse gas emissions and advancing towards a more sustainable energy future. Now let's see how to produce hydrogen by renewable energy or renewable resources. In the recent years, the price of renewable energy has experienced a significant decrease amid fluctuations in oil and natural gas prices. Hydrogen, as we all know, a versatile fuel, can be derived from various energy resources, including both fossils and renewable, as we have discussed in the introduction part. Although the majority of hydrogen is currently obtained through the combustion of fossil fuels, the adverse environmental impact and the depletion of these resources make this method unsustainable. But recent research efforts has focused on developing environment-friendly and contamination-free hydrogen from renewable resources due to their more sustainable nature. So this is the emerging renewable method for hydrogen production. Basically, from any renewable power plant will generate electricity, and on the other hand, water will be supplied in an electrolyzer. From electrolysis or the process of electrolysis will occur, and hydrogen gas along with oxygen gas will be produced. The hydrogen gas produced will be go to a compressor where it will be compressed and transported to for utilization or will go to the storage tank. In my review article, I have stated 6 methods of producing hydrogen production from renewable energy. The first method of producing hydrogen from solar energy. As we all know that solar energy is recognized as the most promising renewable resource for addressing future global needs. And the potential of solar energy to deliver cost-effective electricity bodes well for the production of solar hydrogen as a clean alternative fuel. And to overcome the intermittent nature of solar energy, renewable energy storage techniques are developed. And utilizing solar energy for hydrogen production without greenhouse gas emission provide a practical transition to solar hydrogen. In my review article, I have stated 2 methods of producing hydrogen from solar energy. The first one is photovoltaic energy to hydrogen, and the second one is solar thermal energy to hydrogen. Firstly, we will see production of hydrogen from photovoltaic cell. Generating hydrogen from photovoltaic energy involves a process called electrolysis, which utilizes electricity generated by solar panels to split water into hydrogen and oxygen. So basically what happened actually? Photovoltaic cell or solar cell are used to convert sunlight into electricity. These panels are made of semiconductor materials such as silicon, which generate an electric current when exposed to sunlight through a photovoltaic effect. When sunlight strikes on the surface of the solar panel, it excites electrons in the semiconductor material, creating an electric current. This generated electricity is then directed to an electrolytic system. But the generated electricity from the PV panels is in the form of direct current. So it needs to be converted into alternative current using an inverter, making it compatible with the electronic grid. The electricity produced from solar panels is fed into an electrolyzer, a device specifically designed for water electrolysis. Electrolyzer will split water into hydrogen and oxygen through a process known as electrolysis. Basically, there are different types of electrolyzers, such as alkaline electrolyzers, proton exchange membrane electrolyzers, and solid oxide electrolyzers. We can use any kind of electrolyzer. Each type has its own advantages and disadvantages. Besides this, the generated hydrogen will go to a hydrogen tank for storage or transportation purposes. But keep it in mind that the hydrogen produced may contain impurities and moisture. So some purification steps are implied to remove these impurities and obtain high purity hydrogen. Generating hydrogen from solar thermal energy involves utilizing concentrated solar power systems to produce high temperature, which are used in two-step processes known as generating photovoltaic energy into hydrogen. The second method to generate hydrogen is by using solar thermal energy conversion into hydrogen. Solar thermal water electrolysis for hydrogen production involves using concentrated solar energy to maintain high temperature in a chemical reactor for chemical processes. Generating hydrogen from solar thermal energy involves utilizing concentrated solar power systems to produce high temperature, which are then used in a two-step process known as solar thermochemical water splitting. Basically, concentrated solar power systems use mirror or lenses to concentrate sunlight into a small area, generating high temperature. The concentrated solar energy can be used to heat a working fluid, such as molten salt or heat transfer fluid like oil. The concentrated solar energy is directed to a solar collector, which is designed to absorb and transfer heat efficiently. This collector can be parabolic trough or solar power tower or a parabolic dish depending on the specific system. This solar collector heats or a heat transfer collector its heat into a transfer fluid, which is typically a highly temperature liquid, and to very high temperature, which is often exceeding 500 degrees Celsius to 932 degrees Fahrenheit. This hot fluid carries the thermal energy to the next stage of the process. The high temperature heat transfer fluid is used in a thermochemical process to split water into hydrogen and oxygen. This process is typically a two-step cycle known as a redox reaction. Basically, in the first step of the cycle, the high temperature heat transferred fluid release oxygen from a metal oxide, leaving behind a reduced metal oxide. And in the second step of the cycle, the reduced metal oxide is exposed to a system and oxygen is released, regenerating the original metal oxide. The hydrogen gas produced in the oxidation step is collected for storage or use, and the process can then be repeated in a cyclic manner to produce hydrogen in more. Basically, this solar thermochemical water splitting process has the advantage of producing hydrogen without directly using electricity. As is this case, we have seen that how we can produce energy using solar thermochemical water splitting. The second method of producing hydrogen is using wind energy. Generating hydrogen from wind energy typically involves using electricity generated by wind turbines through a process known as electrolysis. Actually, wind turbines convert the kinetic energy of the wind into the mechanical energy. The rotation of the turbine blades drives a generator, producing electricity. Wind farms often consist of multiple turbines strategically placed to capture maximum wind energy. The electricity generated by the wind turbine is then directed to an electrolyzer for hydrogen production, by which water water is split into hydrogen and oxygen using electricity. The electricity generated by the wind turbine powers the electrolysis system. The hydrogen and oxygen gases produced during the electrolysis are separated to prevent them from recombining. This can be achieved through various methods, such as using membrane or physical separations. The collected hydrogen gas is then stored for later or used or transported for various applications, such as fuel for hydrogen, fuel cells, or industrial processes. It is also important to note that the efficiency of hydrogen generation from wind energy is influenced by factors such as efficiency of the wind turbine, the efficiency of the electrolyzers, and the system losses. Advances in both wind turbine technologies and electrolyzer techniques are ongoing to improve the overall efficiency and sustainability of this method for hydrogen production. The intermittent nature of wind energy may also convert the fluctuation into hydrogen production, and therefore energy storage solutions may be implemented to address that issue. The third method of producing hydrogen is from using water electrolysis. As we all know that water, an abundant molecule in nature, is widely recognized as a significant source of hydrogen. The thermodynamics of a water molecule stand at approximately 285.83 kilojoules per mole under standard temperature and pressure. However, traditional water decomposition through direct heating requires extremely high temperature, which is reaching up to 2000 degrees Celsius. So at such level, the separation of oxygen from hydrogen became impractical. To address this challenge, the utilization of a catalyst, ceramic membrane, and a chemical reactant or energy in water separating process can enable hydrogen production at lower temperature. This figure illustrates the electrolysis of water using a typical electricity source. Basically, what will happen in water electrolysis? The water first will be deionized in a deionizer, and then it will go into electrolyzer. And the other source will be used an electricity, which is first converted into alternative current, and then it will convert it into direct current. The electrolyzer will separate the hydrogen and oxygen. The hydrogen gas produced will be go to storage tank or for utilization purposes. The generated H2 can be then go to for storage or other application, as I stated earlier, and this is a general method of producing hydrogen from water electrolysis. But it's important to note that the efficiency of the electrolysis process is influenced by factors such as the type of electrolyzers, the materials used for electrodes, and the purity of the water or electrolyte solution. And the advances in electrolyzer technology are ongoing to improve the efficiency and cost effectiveness of hydrogen production through water electrolysis. As I explained general method of producing hydrogen from water electrolysis, now we will see some method of water electrolysis to generate hydrogen. The first method is solid oxide electrolysis process. Basically, the solid oxide electrolysis process typically operates within the temperature range of 500 to 850 degrees Celsius. In solid oxide electrolysis process, water in the form of vapor is introduced into the anode, where it is divided into hydrogen gas and oxygen gas as ionic species within the liquid electrolyte. And hence, the hydrogen will be produced. But unlike traditional methods, the solid oxide electrolysis process charges with increasing thermal energy, causing hydrogen gas to escape from the water exchange. Solid electrolytes composed of zirconium stabilized with titanium are employed in the solid oxide electrolysis process. Despite initial challenges related to sustainability and deaeroization depicted in the figure, solid oxide electrolysis process technology had advanced before its commercialization. So as we can see in this figure, there is an electrolyzer at anode. The oxygen gas will be produced, and at cathode, the hydrogen gas will be produced. The membrane is made up of ceramic oxide, or the membrane is ceramic oxide membrane. The hydrogen from the cathode will go to a compressor, and after compression, it will go to a hydrogen storage tank. The second method of producing hydrogen from water electrolysis is using alkaline electrolysis process. The alkaline electrolysis process represents a type of electrolyzer with significant industrial application. It utilizes an alkaline solution, the electrode, to facilitate a reducing reaction, resulting in the production of one molecule of hydrogen and two molecules of hydroxyl ions. In this process, hydrogen gas is generated at the cathode surface with hydroxyl serving as an intermediate. Hydroxyl ion is then transported to the anode, where it is converted into oxygen gas and H2O liquid. The oxygen gas products at the anode surface can be easily separated from the hydrogen liquid phase. The addition of a chemical such as 20 or to 30% of sodium hydroxide solution as an electrolyte enables water electrolysis to occur at a lower temperature of about 30 to 80 degrees Celsius, a technique which is known as alkaline electrolysis, as you can see in this diagram. Aspartate and nickels are commonly used as a membrane and electrode, respectively, in water electrolysis cell, with a diaphragm situated between the cathode and anode to separate gas molecules, or to separate hydrogen and oxygen gases molecules. The third method of producing hydrogen is using alkaline electrolysis process, or the proton exchange membrane electrolysis process. This process is the same as alkaline electrolysis process. Instead of a diaphragm, we will use a polymer membrane. And instead of hydroxyl ion, the hydrogen ion will be used. Researchers have explored the proton exchange membrane electrolysis process as an alternative strategy for hydrogen production, which is focusing on proton exchange membrane instead of Africa diaphragm, as I told you earlier. This novel approach aims to address serious challenges associated with alkaline electrolysis. Proton exchange membrane electrolysis process operates at temperature below 80 degrees Celsius, utilizing proton or hydrogen ion as the ionic species, as I told earlier. The fourth method of producing hydrogen is using geothermal energy. As we all know that geothermal energy stands out as one of the most reliable and consistent renewable energy source due to the independence from the surrounding environment. It can be stored as a heat in the Earth's underground substructure. This renewable energy source has been industrially utilized in the regions where access to underlying substructure is challenging, mainly due to drilling costs and other constraints. However, nations nowadays with abundant geothermal energy supplies and lower pumping costs have not fully tapped into this resource. And extracting geothermal energy from underground deposits to a surface requires a heat transfer carrier, which is achieved in two phases. First is heat transfer through the conduction of heat among rock formations, and then its excess heat is supplied to the ground through heat transfer rates. And utilizing both shallow and profound geothermal systems, this source serves various purposes, including cooling, heating, power production, and energy storage. Geothermal energy also emerges as a solution to growing environmental problems and align well with hydrogen production while remaining completely private. In this review article, I have implied the common method of utilizing geothermal energy for hydrogen production involves geothermal flood and leftover heat to heat water or using high temperature electrolysis as exposed by several authors. Thermodynamic analysis have shown energy efficiency above 80% for hydrogen synthesis. So basically, what happens in the production of hydrogen from geothermal energy? In a flat separator, water and steam in first process, where steam is utilized to produce power through a steam turbine. Simultaneously, energy collected from heated water via an exchanger is used to generate more energy for hydrogen production. as we can see in this figure. Firstly, we have a production well, a flat separator, which will convert or split the water into steam with the help of a flat separator. Then the steam will turn the steam turbine, and isobutane turbine will also be attached to the steam turbine, which will generate the hydrogen. Then the hydrogen will be pumped into an air cooler condenser it will be condensed, and then with the help of electrolyzer, the hydrogen and oxygen gases will be produced. This is the schematic diagram of hydrogen production from geothermal energy. So thank you. This is all for our first video. In the next lecture, or in the next presentation, we will study other parts of hydrogen production method and environmental aspects.